Hey everyone, welcome back for another deep dive. Today we're going deep on how language models remember what they've read.
Yeah, we're talking about a very specific type of memory called MQAR. That's multi-query associative recall.
MQAR.
And you can think about it like this. Imagine you're reading a huge code base with variables all over the place.
Okay,
To understand it, you need to keep track of what each variable means, even when its definition is pages away.
gotcha. So like I'm constantly having to flip back and forth to
Yeah.
remember what each variable represents.
Exactly. And that's basically what MQAR is all about for language models, being able to make those connections even across long distances.
That makes sense, and it sounds like a pretty crucial skill for any language model that's going to be working with real-world data.
It is. It's essential for things like generating code, answering questions about long documents,
But
all sorts of tasks.
so how do they do it? How do these models actually perform MQAR? Are some better at it than others?
Well, it all comes down to the architecture of the model. You know how it's designed. And one of the dominant approaches right now is the transformer architecture.
The transformer, yeah, those are pretty famous, thanks to models like ChatGPT and all that.
Exactly. And transformers have this incredible ability called attention.
Attention. I've heard that term thrown around a lot, but could you break down how it actually works?
Sure. Think of attention like giving the model a spotlight that it can shine on any part of the text. It's already seen even stuff way back at the beginning.
Right.
So if it needs to figure out what a variable means, it can just shine that spotlight back to where it was defined no matter how far away that is.
So it can directly compare those two pieces of information, the variable and its definition, even if they're pages apart.
Exactly. And that's what makes transformers so good at MQAR. They have this direct connection mechanism through attention.
Sounds pretty powerful, but I'm guessing there's a trade-off somewhere. Nothing's free in the world of computing.
You're right there is that flexibility comes at a cost, computationally speaking. The more information the model has to compare, the more resources it needs, the more compute power and memory.
Makes sense.
And the resources needed for attention actually grow quadratically with the input length.
Quadratically meaning,
If you double the length of the text, you need 4 times the computing power.
oh wow, so it scales up really fast.
Yeah, and that's why researchers are looking into more efficient alternatives to transformers, particularly for very large inputs.
Interesting, like what kind of alternatives are we talking about?
Well, 2 promising approaches are gated convolutions and linear attention models.
Okay, those sound pretty technical.
They are, but the basic idea is they try to be more computationally frugal by using some clever tricks.
But I'm guessing they're not as good at MQAR as the transformers.
You're right. They do seem to struggle a bit compared to transformers, and particularly those gated convolutions have a hard time with really long-range connections.
I see. So it's like a classic trade-off between power and efficiency. But can you explain a bit more about how these gated convolutions actually work and why they might have trouble with MQAR?
Sure, imagine you have a line of words and you want to find connections between each word and the word 4 positions ahead.
Okay, 4 positions ahead.
A convolution does this by shifting the sequence, so you can compare the original sequence to the shifted one.
Okay, so like moving the words over by 4 spots.
Exactly. And think of it like taking a piece of paper with a list of words, folding it to align words 4 positions apart, and then seeing which ones overlap.
Okay, I can kind of picture that. So that's the convolution part. What about the gated part?
The gates act like filters controlling which information gets passed along.
Ah, so they're like checkpoints along the folded paper, only letting certain words through.
Right, and the problem is that to handle all the possible connections in a long text, each hidden state, which is like the model's short-term memory, has to store information about all the words.
Oh, so it's like trying to cram an entire encyclopedia into a tiny little box.
Yeah, at some point you run out of space, and that's where these efficient models start to hit a bottleneck.
Fascinating. So even with these clever tricks, there are still some fundamental limitations.
There are, and researchers are using a rather surprising tool to try and understand these limitations better.
Okay, now I'm really intrigued. What tool are we talking about?
Arithmetic circuits.
Arithmetic circuits. Now sounds pretty intense.
Yeah.
How does math help us understand language models?
Think of an arithmetic circuit like a blueprint for how a model computes broken down into really simple steps.
Okay.
It shows how the model combines information step by step, kind of like a recipe for the model's calculations.
So it's like we're getting this X-ray vision into the model's brain.
Exactly.
Yeah.
And by analyzing these circuits, we can get a better understanding of a model's complexity, its efficiency, and even its potential limitations.
So what have researchers learned about these efficient models and how they handle MQAR? by looking at their arithmetic circuits?
Well, one really interesting finding is that a lot of these efficient models, including those gated convolutions, can be represented by a specific type of arithmetic circuit called basecon.
Basecon, huh?
Yeah, you can think of it like a common language for describing different models, makes it easier to compare them head to head.
So it's like we're translating all these different model designs into a single framework.
Exactly, and that's really powerful because it lets us see the underlying similarities and differences between these models in a much clearer way.
That's pretty neat. So what have researchers learned from this about MQAR and those more efficient architectures?
Well, it's revealed both some interesting insights and some pretty hard limitations.
Oh, okay.
While basecon is very versatile, it can represent a wide range of models, it does have its limits, especially when it comes to MQAR.
In what way?
The researchers were able to mathematically prove that efficient models using a fixed amount of memory really struggle as the input sequence gets longer.
So the longer the text, the harder it is for them to keep track of all the connections.
Right. There's this fundamental trade-off between memory usage and recall quality.
So even with all these clever circuit designs, we're still hitting a memory wall.
Pretty much, it seems like if you want really good MQAR performance, you need those powerful but resource-hungry transformers.
But I'm guessing the research doesn't just stop there, right? I mean, researchers are always looking for ways to push the boundaries.
Oh, absolutely. Just because we've found some limitations doesn't mean we give up. There's some really exciting new directions being explored.
Like what?
Well, one promising area is multi-pass recurrent models.
Multi-pass recurrent models.
Okay.
I'm not familiar with that.
So unlike traditional language models that process text in a single pass from left to right, these models can actually go back and revisit earlier parts of the input multiple times.
Oh, so they can like reread sections if they need to?
Exactly, like we might do with a complex book. You go back and reread a paragraph to make sure you understand what's going on.
That makes sense. So it's like they're getting a second chance to process the information and maybe pick up on connections they missed the first time around.
Exactly, and this ability to revisit information might allow models to use their limited memory more effectively.
Instead of trying to cram everything in at once, they can focus on the most relevant parts. Kind of like how we selectively pay attention when we read.
Right. It's all about being more strategic with their memory usage.
So it's not just about brute force computation, it's about finding smarter ways to learn.
Precisely. And the initial results with these multi-pass models are really promising. It seems like allowing models to think more deeply about the input could lead to some significant improvements in efficiency and performance.
So maybe there's hope for these efficient models to get better at NQAR after all.
There definitely is. It's still early days, but this research is really exciting. It shows that we're not just stuck with those limitations, we can find ways to overcome them.
This has been a fascinating deep dive so far. I'm really starting to appreciate the complexity of what we're asking these models to do.
It's a challenging problem, but it's also incredibly rewarding to see the progress that's being made and the creativity of the researchers working on it.
Yeah, it really makes you appreciate like how complex our own brains are. We do this stuff without even thinking about it.
I know. It's amazing how effortlessly we can connect information and make sense of things, but trying to replicate that in a machine turns out to be really, really hard.
Yeah, and the fact that researchers are using these tools like arithmetic circuits, these abstract mathematical concepts to analyze these models, it's just incredible to me.
It really shows how much progress is being made in this field and how researchers are finding really clever ways to understand and improve these models.
It's like we're breaking down these black boxes and actually seeing how they pick.
Exactly. And I think that's a key takeaway for our listeners. As AI becomes more and more prevalent, it's important to understand not just what these models can do, but also how they work and what their limitations are.
Right. It's not enough to just see the amazing results. We need to understand the process behind them.
And I think that's what makes this research so fascinating. It's not just about building bigger and faster models. It's about really understanding the fundamentals of learning and intelligence.
And who knows what amazing new capabilities will be unlocked in the future. Maybe we'll have models that can not only remember vast amounts of information, but also reason and learn and even create in ways that we can't even imagine right now.
The possibilities are really endless, and I think that's what makes this such an exciting time to be following this field.
Well, that brings us to the end of another deep dive. We hope you enjoyed this exploration into the world of MQAR and arithmetic circuit complexity and the quest for more efficient and intelligent language models.
It's been a pleasure diving deep with you.
And to our listeners, until next time, keep those minds curious and stay tuned for more fascinating deep dives into the world of ideas.